Thank you very much. Thank you very much to the organizers for organizing such amazing, exciting, intense conference. I'm quite tired. I'm sure a lot of you are quite tired, so let's try and have some fun. Let's begin with some motivation. This is a classical result from model theory. So suppose we have two first-order theories which are countably categorical. That means there is, up to isomorphism, a unique countable model. Then if we take those countable models and we consider the topological automorphism group of those models, then our two theories are bi-interpretable, and I've got some interpretation of what bi-interpretable means. In reference to Marco Panzeri's talk earlier, this is bi-interpretable in the model theoretic sense, which is slightly wider than the sense he used. Two theories are bi-interpretable if and only if the topological automorphism groups are homeomorphic. So this means that we can start applying techniques from topological group theory in order to understand first-order logic. And this has been very fruitful. Just a few examples. Combinatorial group theory has played a role, and continuous group cohomology has also been used to study aspects of theories, and I recommend everybody go and read the survey article by McPherson if you're interested. I want to ask how we can generalize this result. If we don't use the unique countable models of our theories, then we're going to have to weaken the homeomorphism condition. We're going to have to consider something weaker than homeomorphism of topological groups. And if we remove the countable categoricity condition, we're no longer going to be able to use topological groups. We'll have to use something more general. I want to emphasize that this is an active area of research outside of topos theory, outside of category theory. Just recently, a few years ago, Ben Yaacov has given, let's say, the model theorist's perspective on how to generalize this Ahlbrandt and Ziegler result. He came up with a topological groupoid where it had this property that the topological groupoid corresponding to a theory characterizes that theory up to bi-interpretability. I will mention that the groupoid he uses is not a groupoid of models, so what you'll see today is orthogonal to his development. So, how would a topos theorist choose to generalize this result from model theory? Well, there's going to be some toposes. To every first-order theory, we can assign it a classifying topos. And we're going to be using topological groupoids. For every topological groupoid, we can also assign it a topos, the topos of equivariant sheaves, or just sheaves for short. And so we can come up with some definition and say that, okay, my theory is going to be represented by a topological groupoid if these two toposes are equivalent. And then we have a tautology, which we could maybe think of as a theorem template, that two theories with representing topological groupoids are Morita equivalent, meaning that their classifying toposes are equivalent, if and only if the topological groupoids are Morita equivalent, meaning their toposes of sheaves are equivalent. And you know, this is just a tautology at this point, but the point is that if we understand Morita equivalence for theories when a theory is represented by a groupoid and Morita equivalence of groupoids, then we're going to get not a theorem template, but maybe something which we can actually go out and apply in the wild. So this can all be visualized as a bridge diagram. The sort of questions we need to answer when two theories are Morita equivalent. Hopefully everybody's kind of au fait with what that means. We need to understand when a theory is represented by a topological groupoid, and then we need to understand Morita equivalence of topological groupoids. So the first one can be sort of taken as a definition, but let's just say that there's been some recent interest by non-category theoreticians, logicians from a traditional background, in Morita equivalence as a constructive extension of bi-interpretability, but they've also shown that the model theorists are going to be happy when we throw in some classical assumptions. Morita equivalence is going to coincide with bi-interpretability. For this keystone property in the middle of our bridge, we do have a characterization of when open topological groupoids represent a particular theory. Unfortunately, I won't have enough time to speak about that today. Instead, today's presentation is going to be about the third component, about Morita equivalence of topological groupoids. So, let's see the theorem. Two logical groupoids, which is going to be topological groupoids satisfying some properties, have equivalent sheaf topoi, that is, they're Morita equivalent, if and only if there exist embeddings of these two logical groupoids, continuous embeddings, into a third logical groupoid, which is going to satisfy some very stringent properties. And the outline is we're going to first see a definition of what it means to be a logical, We're going to first look at I told you I was tired. We're going to first look at the sheaf toposes on a topological groupoid, then we're going to see the definition of a logical groupoid, and finally, we'll explain what I mean by these continuous embeddings, which are weak equivalences. Okay, so let's carry on. A topological groupoid is a groupoid in the usual sense, where when we expand it out as a diagram of sets in this way, so x0 is my set of objects, my groupoid, x1 is the set of arrows, and then this pullback is the set of composable pairs, and then these arrows represent source, target, identity, composition, the inverse because we're in a groupoid. It's going to be a topological groupoid if x0 and x1 can be endowed with topologies such that all of those arrows become continuous. And it will be used later. I'm going to say that a topological groupoid is open if the source map, or equivalently the target map, is open as well as continuous. Okay, so if we've got a topological groupoid, well, let's just start off with a groupoid. If we've got a groupoid, we can consider what it means to be a bundle over that groupoid. So that is, we're just going to have a bunch of stalks living over my set of objects, and I've got a lifting of the action of the arrows to an action on my stalks, satisfying the properties one would expect of an action. And then if we do indeed have topologies making X a topological groupoid, then we're going to say that this bundle is a sheaf if this projection downwards is a local homeomorphism and the action is continuous. A morphism of sheaves is going to be a continuous morphism of bundles, which is equivariant with respect to the given action. And when we put all of that together, we get a topos, which we're going to call the topos of sheaves on our topological groupoid. So we can see that this generalizes some well-known examples of toposes. In particular, if we have a topological group, that's a one-object topological groupoid. Its sheaves corresponds to the familiar topos of continuous actions on discrete sets, which is normally written as BG. So I've stuck with that in this presentation. Okay, so that was sheaves on a groupoid. And now let's turn to logical groupoids, this restriction of topological groupoids we're going to consider. Now, before I introduce the definition of logical, I want to talk about the group case and use this as some motivation for the definitions which are going to occur. So if we have a topological group satisfying a nice separation axiom, T0 is sufficient, then we're going to have the following equivalent conditions. It means that if you have any two distinct points, there is an open set containing one or the other. These are equivalent conditions for such a topological group. Firstly, the open subgroups are a basis of open neighborhoods for the identity. In Roy Hora's talk, this was called nice enough topologies. The second equivalent condition is that the topology on our topological group is the coarsest topology determined by the topos, BG. That is to say, if we have another topology on our topological group, well, if we have another topology on the underlying group, and if the topos of continuous actions of that new topology and the topos of continuous actions for the old topology, if those are canonically equivalent, then our original topology is going to contain the new one. It's the coarsest topology determined by the topos. And then the last condition should maybe signify why the word logical is being thrown around. The other equivalent condition is there exists some set such that our topological group is a topological subgroup. It is a subgroup endowed with a subspace topology for the group of permutations on that set, where we endow that group with the pointwise convergence topology. That is the topology which is generated by cosets of stabilizers of finite tuples of that set. Okay, so hopefully that should explain why we're using the name logical and why this is a relatively natural condition to impose. And we're going to generalize point 2 for our definition. We're going to say that a topological groupoid is logical if the topologies involved are T0, if it's an open topological groupoid, and the topology on our space of arrows is the coarsest such topology determined by the topos of sheaves, in a manner analogous to the case for groups. Maybe just a remark on this definition that I won't explain all of the detail, well, I won't explain any of the details actually, but point 3 also generalizes to the groupoid case. I'm not aware of how to generalize point 1, so maybe someone cleverer than me can help me afterwards. That's logical groupoids. Now let's look at these weak equivalences I alluded to earlier. So if we start off with a topological groupoid, and if we have any two subgroupoids of that groupoid, then each arrow in our groupoid X comes equipped with an action on the left and the action on the right by these subgroupoids, given by post-composition and pre-composition by the arrows in those subgroupoids. So because we've got this action on both sides, we can consider the bi-orbit of each arrow. So that is going to be all of the arrows we can get to by pre-composing and post-composing by arrows contained in the specified subgroupoids U and Y. And because everything's topological, there is a quotient map to the space of bi-orbits until we can endow, well, the set of bi-orbits until we can endow it with a quotient topology to get a space of bi-orbits. And now, here comes the main theorem. If we have a logical groupoid and a subgroupoid endowed with the subspace topologies, the inclusion of Y into X induces a equivalence of their sheaf topoi if and only if this, for every open subgroupoid of X, this continuous map is a quasi-homeomorphism. So, let me explain a little bit what's going on in this continuous map. This is the subspace of bi-orbits by U on the right and Y on the left, where every representative, the source of that representative, begins in U and it ends in Y. So that's a subspace of a space of bi-orbits. And then here, notice that we're taking a different subgroupoid. We're expanding to taking bi-orbits by U on the right and X on the left. And this is the subspace of bi-orbits where the source begins in U. And a quasi-homeomorphism, the name should suggest it's almost like a homeomorphism. It's a continuous map where the inverse image acting on opens is a bijection. So if these spaces were sober, that would be equivalent to being a homeomorphism. These quotient spaces tend not to be sober. Okay. And so any such continuous inclusion of a topological subgroupoid satisfying these hypotheses we'll call a weak equivalence. Let's move that over to one side and think about the particular case of a logical group, because I think that would illustrate that when we simplify to certain cases, such as the logical group, things actually become a lot nicer. So for logical groups, these conditions simplify to say that my topological subgroup is a dense subset, G. Okay. And from this theorem, we have to add in an extra fact that says you can always expand your space of objects for a topos of sheaves. But we sort of get out quite easily the corollary, which says that two logical groupoids have equivalent sheaf toposes if they can be embedded by these weak equivalences into a larger into a larger logical groupoid. And so now we can then get our extension to Ahlbrandt and Ziegler, which says if we have two theories with some choice of representing logical groupoids, then those two theories are Morita equivalent if and only if we have such a co-span of weak equivalence embeddings into a third logical groupoid. So that concludes my presentation. Thank you very much.